In this class session, we're going to review material from chapter 8. And that has to do with chemical composition. The composition of a chemical is what it's made of and how much it's made of. And with an eye to the future of reacting one chemical with another and understanding that those reactions only occur between atoms, molecules, ions. They don't occur between masses, but we need a connection between the mass and the molecule, or the atom, or the ion. And that's what we covered in chapter 8. All right, so let's do a little review here. I'm going to use the review document that is available on Brightspace. And let me give you a look-see. Right, this is what it looks like. All right, it's a little out of focus. Anyway, I've chosen some and highlighted some. And what I'm going to do first is share the screen with that document in it. Go. All right. And then I need to take a second and get the classroom to join. Bear with me. Okay. Okay. Let me make that just a hair bigger. There we go. All right. So you've noticed I've highlighted some of these from that document. And those are the ones we're going to focus on. When you work through the review document, you'll notice that there's a lot of repetition. There are different types of problems, but there are a lot of the same problems. So what I've done is I've gone through and marked out some that are different from their neighbors so that you can get a taste of everything that's in the document. All right. So let's start with number 1. The number of grams in 2.58 moles of sodium carbonate is. So we're given 2.58 grams of sodium carbonate. When you see the name sodium carbonate, that does not give you enough information for solving a problem. What you need is a chemical formula. That's why it was so important in the beginning to learn how to write the formula from the name and the name from the formula. If you haven't mastered that technique yet, you need to catch up. Sodium carbonate. We have sodium, and carbonate is a polyatomic ion with a 2- charge. Sodium is an alkali metal with a 1+ charge. So in order to balance the charges, we need 2 sodiums. Right? So when we write the compound, we generally don't put the charges in. That was just for bookkeeping. Now that we have this much, we can say, all right, if we're going to convert these to grams, we need a conversion factor. Right? Denominator, numerator, they cancel. And moles, oh, excuse me. It's 2.58 moles. My mistake. Let's get this right. We want to convert this to grams. So moles goes on the bottom, grams on the top. Okay, so what's the magic number? The molar mass of sodium carbonate. That's why you have to know how to write that formula. Otherwise, you can't calculate the molar mass. So we need to look at your periodic table. Sodium is 23, yeah, 23 grams per mole. Carbon is 12.01. Look it up or take my word for it. And oxygen is 16 grams per mole. Then we add all those together. And that's the molar mass of that compound. So that's 106.01 grams per mole. Right? As it turns out, grams on top and moles on the bottom is what we want. There we go. So now, that's the hard part. That's the thinking part. The rest is just number crunching. So we say this value times that value gives us the grams. 2.58. So that's 273.51. And let's see, we can have three significant figures. Remember, conversion factors are exact numbers. They don't limit the number of significant figures. This value does limit. So we have to round that to 274. All right. So that's why the answer is D. All right, I spent a lot of time on this one to make several points. When we work through the rest of these problems, we're not going to take as much time explaining why I do certain things. This is a conversion factor problem, and you have to get the conversion factor from the formula that you write based upon the name. All right, number 2. 8.52 grams of water. 8.52 grams of water is what we're given. How many molecules of water? All right. One conversion factor is not going to get us there. We've got to bridge the gap between mass and numbers. And that bridge is molar mass. Grams on the bottom, oops, moles on the top. Okay, we've calculated this one so many times. You just need 2 hydrogens and 1 oxygen. So 2 times 1.01 plus 16 is 18.02. That's the molar mass of water. That gives you moles. Okay, the question is molecules. Now we need another conversion factor to go from moles, right, numerator, denominator, to molecules. So what's the magic number here? Avogadro's number. There are 6.022 times 10 to the 23rd molecules in a mole of anything. Right? Now we've done the thinking part. We just do the calculations and we should come out with, in the interest of time, I'm going to just defer to the answer. 2.85 times 10 to the 23rd. Molecules of water. All right. And there's 3 significant figures there and 3 there. All right, let's scroll to number 3. How many moles of aluminum oxide are present in 78.8 grams of this compound? 78.8 grams. And they're giving you the formula. Aluminum oxide. Now, why is it aluminum oxide, not aluminum 3 oxide? Okay. Because this is not a type 2 compound. This is a type 1 compound. Aluminum has a fixed charge. So putting a 3 in there would be redundant. That's all that's required. And we know exactly how to write that from this or this from that. All right, next we want to calculate the moles of aluminum oxide. So we need grams on the bottom, moles on the top to give us moles. Okay, what's the molar mass of aluminum oxide? Well, we need 2 times aluminum, 2698. And I'm getting that value from the periodic table. Okay, add those together. It's 101.96. All right, divide that into 78.8, and I get 0.77285. That's what my calculator says. How many of those can I keep? Just 3 significant figures. Right? So we'll pare it down. Let's see. The answer is given in, it's a mix. So we'll leave it here until we get a standard notation answer, 0.773 moles. Now, is that one of the answers? Yeah, it is, A. Right? So we don't have to convert it to scientific notation. All right, number 4. Which of the following compounds has the greatest percent by mass of oxygen? Now, this one's going to take some work. And for this type of problem, I use Henry Ford. Set up an assembly line. So we have A, B, C, and D, and E. All right. Write the formula for the compound. Potassium carbonate. All right. 2 minus, 1 plus, that means we need 2 there. Next one. Nitric acid. So you start with nitrate. 8's become X. There's your nitric acid. Okay. Zinc 2 oxide. So we have a zinc with a 2 plus charge and an oxygen with a 2 minus. That's it. That's all you need. Sulfur dioxide. This is a type 3 compound because both of the components of the binary are nonmetals. So 1 sulfur and 2 oxygens. And the last one, diphosphorus pentoxide. We need 2 phosphorus and 5 oxygens. All right, let me clean this up a little bit. There. Okay, now we have our formulas. In order to determine the percent by mass of oxygen, we need the total mass. We assume, for the purposes of calculation, that we have 1 mole of each one. If we have 1 mole of each one, then we have 3 times 16 grams of oxygen in the total, which is 3 times 16 plus 1 times 12.01 for carbon plus 2 times 39.10. for potassium. And then percent is times 100. Okay. That's the same pattern we use for each one. Right? For nitric acid, we have 3 times 16 for the oxygens. Then we have 3 times 16 because just because you put the oxygen up here doesn't mean you destroy it and you can't put it down here. This is the total mass. This is just the mass of oxygen. Plus 1 times nitrogen. And then 1 times hydrogen, 1.01 times 100. See, we're doing the thinking part first, and then the rest is just crunching numbers. Zinc and oxygen, right? 1 oxygen on top, 16. Then the oxygen on the bottom plus the zinc. So we go to our periodic table, and zinc is 6538. 6538 times 100. Okay, sulfur dioxide. Okay, we've got 2 oxygens in the numerator, 2 oxygens in the denominator, plus a sulfur, which is 3207. Just one of them. And then diphosphorus pentoxide. Now we're going to have 5 oxygens in the numerator and 5 in the denominator. And then 2 phosphorus, which is 3097. Okay, so now the rest is just banging their fingers on the calculator. All right, so 3 times 16 is 48. And then we're going to add 12.01 and 2 and 39.10. Add those together. So that's 138.21 in the denominator and 48 in the numerator. I'm going to divide times 100. And I get, well, all of these are exact numbers. So we can pick the, I'm going to say 34.7% oxygen by mass. All right, again, 48 at the top, 48 at the bottom, plus 14.01, plus 1.01, and then divide, and then 100 times that is 76.2. Okay. Now we got 16, 65.38 added to that in the denominator, divide times 100, we got 19.7%. Now 32, 2 times 16 is 32. And then 32.07 plus that one divided into the numerator times 100 is 49.9. And then the last one, 16 enter in 5 times, and then to 30.97. Add those together and then divide 100 is 35.2% oxygen. Okay, what was the question? Greatest percent by mass. The greatest percent by mass is this one. Nitric acid. Okay. Now that took a lot of busy work, but really it's the same calculation for each one. We just put the right values in their proper place based upon the formula. So the hard part is getting the formula right first. And then you're busy for a while getting these numbers. That's why I set them up in assembly line, because you do them the same way each time. Then you compare your results. All right, number 5. Okay, compound X2Y is known to be 60% X by mass. X2Y is 60% X, 60% X by mass. Calculate the percent Y by mass of the compound X2Y2. Okay. So let's say, let's do it this way. This is 60%. This is X2, Y2. And the question is percent Y by mass for this compound. So this is the question, this one right here. So what's the percent Y for this one? The percent Y would be 40%, wouldn't it? That would make a whole 100%. All right. So we can't work with percent. We need mass. So what's the mass? Well, let's assume that assume 100 grams. In that case, we have 60 grams here, 40 grams here. Okay. How much does Y weigh? Well, it's 40 grams. Right? That's 40 grams. For one Y. So this means 80 grams. For two Ys. Well, we're looking for the percent. So we've got 80 grams here. This means that this X is still 2. So we've still got 60 grams here. That means the total is 140 grams. And the percent Y then is 80 divided by 140 times 100. Right? So let's see what that is. 80 divided by 140 times 100 is actually 57%. Okay. So that's D. Now, I hope that made sense. All these ratios are fixed for each compound. And we're just finding out what one value of X stands for, which would be 30, but there's still 2 of them, so that means it's 60, contributing from this side. One value here is 40, but you got 2 of them over here. And the total mass now of that compound is not 100 grams, it's 140 grams, because we have 2 Ys instead of 1. Then you calculate the percent. All right. Moving along, let's see, we're going to skip some redundant ones there and get down to 12. All right. What's the mass of 5.826 moles of calcium hydroxide? 5.826 moles of calcium hydroxide. There's only a slight difference in this one than a previous problem, and that is the parentheses. When you calculate the molar mass of this compound, you must count for 2 oxygens and 2 hydrogens. So calcium is 40.08. 2 oxygens would be 32, and 2 hydrogens would be 2.02. So we'll add those together and get our conversion factor for this one, because the question is, what's that mass? When you have mass and moles in a ratio, it's always molar mass. 40.08, 32, and 2.02. So that's 74.1. There we go. Moles cancel, leave us with grams. So if we do our calculations correctly, that should come out to 431.7 grams. 4 significant figures, 4 significant figures. All right. That was number 12. 13. All right, choose the pair of compounds with the same empirical formula. Remember what the empirical formula was. It's the simplest whole number ratio of elements in that compound, right? So what we're looking for is two things. Each of those compounds must have the same two elements or the same two parts to the binary. And one must be a whole number multiple of the other one. All right. So let's look at them one at a time. A, water and hydrogen peroxide. Okay. This can't be simplified anymore. That's the empirical formula and the molecular formula for water. This one can be simplified to HO, right? And we just have to multiply it by 2 here. So HO and H2O are not the same. How about B? C2H2 and C6H6. What's the empirical formula for this one? CH. And this one, CH. This one would be multiplied by 2 and this one by 6. The empirical formula is CH. This one is the correct answer. And the reason we don't need to look at the rest of them is because they're all unique answers. And we worked our way down and found the right answer. We're done. Mark the answer, move to the next question. Because time is expensive in an exam. All right, let's go to 15. Okay. What's the molar mass of barium hydroxide? Well, it's almost like we're running backwards, isn't it? Barium hydroxide, right? So you need barium. One barium is 137.33. 2 oxygens and 2 hydrogens, right? Add those together and you should get 171.35. Right, that was simple. $16. Calculate the number of molecules in 0.000400. 0.000400. See if I got enough zeros in there. Yeah, grams of gaseous oxygen. Grams of oxygen. Okay. Number of molecules. If I've got that many grams, we need to convert first to moles. And then we can convert moles to molecules. 6.022 times 10 to the 23rd. And the oxygen here is 32 grams per mole. Because each oxygen is 16, and you have 2 of them. Right? So grams cancels here, moles cancels there, and leaves us with molecules. We do the calculation, and we can have 3 significant figures, right? These zeros are not significant. But these zeros are significant because of that explicit decimal point. All right, so we have three significant figures, and if we do calculations right, it should be 7.53 times 10 to the 18th molecules. All right, 16. Uh, 17. Go. 22.6 grams of copper represents how many moles? All right, 22.6 grams of copper. How many moles is that? Right. We just need the molar mass of copper. 3.55. Yeah, 63.55. Right. Grams cancel, leaves us with moles. We can have 3 significant figures in the answer. And if I do the calculations correctly, it's 0.356 moles. Now, is that reasonable? Okay. So what would be 20 divided by 60? Right? Approximately 20, approximately 60. That would be a third, right? 0.3. Yeah, it's a reasonable answer. All right. 19. Calculate the number of moles of chlorine molecules in a sample that contains 7.380 times 10 to the 25th molecules of Cl. Okay, 7.380 times 10 to the 25th molecules. Now, all it wants to know is how many moles is that? We're going from this expression of numbers to another expression of numbers. So it doesn't matter that it's chlorine. It could be anything. It could be oxygen. It could be gold. Doesn't matter because we're only going from numbers to numbers. It's not specific for chlorine. So the only conversion factor we need is Avogadro's number. Molecules per mole. Right? And that's going to give us 4 significant figures is 122.6. 122.6 moles. Okay. 22. All right, acetylene gas. 92.3% carbon, 7.7% hydrogen, and its molar mass is 26 grams per mole. What's the molecular formula? Remember, when we have the percent by mass of elements in a compound, we can calculate the empirical formula. No problem. But we cannot do the molecular formula unless we know the true molar mass of the compound. And that's given to us there. So we've got both pieces of information that we need. All right, so acetylene is 92.3% carbon and 7.7%. Oops. Let's get this over. 7.7% hydrogen by mass. Okay. The first hurdle, remember, is percent is a dimensionless number. It's parts per 100. But we do know that it's grams per 100 grams. But we cannot convert percent to moles. And in order to write the empirical formula, we have to know the mole ratio of the elements. So what we're going to do is assume 100 gram sample. That means 92.3 grams per 100 grams is percent by mass. And 7.7 grams per 100 grams is percent for hydrogen. All right. Now we need to convert these to moles so we can get a mole ratio. Right. Carbon is 12.01 grams per mole. And hydrogen is 1.01 gram per mole. Okay, so we get a value there. 92.3 divided by 12.01 is 7.685 moles. And 7.7 divided by 1.01 is 7.624 moles. All right. Remember, the law of definite proportions says the compound is fixed in mass ratio. So this mass to this mass is fixed for acetylene. That means that the mole ratio is also fixed once we convert that to moles and moles. So it's 7.685 moles for every 6.624 moles of hydrogen. Well, we're looking for a whole number ratio. What we normally do is take the smallest one, like this, 7.624, and divide it in to each one. That gives us the same ratio, but we're approaching whole numbers. This one is very close to that one. So that's almost 1, isn't it? That's close enough. So the empirical formula is carbon, hydrogen, like that. Now, in order to do the molecular formula, we need a multiplier. So the way we do that is we ratio the weights, the molar masses of each formula. The molar mass of this formula, I call the empirical weight, is 12.01 plus 1.0. So that's 203 grams per mole for that species. We're given 26 grams per mole, 26.02, no, just 26 grams per mole. This is the molecular weight, the molar mass, and this is the empirical weight, right? So if we multiply that one times 1, we'll get this. If we multiply it times 2, we get this. So N equals 2. And the molecular formula then is C2H2. Right there. '24. The molar mass of ammonium phosphate is. All right, here's another one where you have to know how to write the formula. Ammonium is not an element. It's a polyatomic ion. Ammonium is like that. Phosphate is a polyatomic ion, like this. Right. So to balance it, we need 3 of these ammoniums, but we cannot change the subscripts. This whole group right here has that positive charge distributed over the whole. So that means we need a parentheses and a subscript of 3. Now we can calculate, right? 3 nitrogens, 14.01. 3 times 4 is 12 hydrogens. 1 phosphorus, 3097. And 4 oxygens. Right? Multiply those out, add them together, and you should get 149.09. Oops. Grams per mole. There we go. All right. It all hinges on your ability to write the formula for the compound. 27. 26.4 grams of nickel represents how many atoms? All right. This is going to be a chained conversion, 26 grams of nickel. Right? We need the bridge, the conversion factor that goes from mass to numbers. And that's molar mass. So nickel is 58.70. I've got rid of the grams. Now we need to change the moles to atoms. Okay, there we go. That's the hard part, the thinking part. Now we just crunch the numbers. Well, in the interest of time, I'm going to defer to the answer sheet. 2.71 times 10 to the 23rd. Atoms of nickel. Now, we did need to know the molar mass for nickel in this case. Our previous example of chlorine, we didn't need to know it because it was already in numbers. But this one, we had to convert to numbers first. Then we could get atoms with Avogadro's number. All right. Next. 31. What's the mass of 8 atoms of copper in grams? 8 atoms of copper. All right. Our bridge to mass is moles. We have to convert this to moles first. All right. Numerator, denominator. And this is moles. 6.022 times 10 to the 23rd. Right. Now that we have moles, we can convert to grams. We just need the molar mass of copper, which is 63.55. Okay. And if we do the calculations correctly, we should get 8.44 times 10 to the minus 22 grams. That's how much 8 atoms of copper would, that's the mass of 8 atoms of copper. Let's see, we'll skip a few that are redundant. I marked that one out because it's not supposed to be there. 43. .98 moles of sulfur trioxide molecules contain how many oxygen atoms? All right, 7.98 moles of sulfur trioxide. All right. There are a couple of ways you can solve this. First, I want to convert this to molecules of sulfur trioxide. Okay. We need Avogadro's number. That gets rid of that one. That's how many molecules of sulfur trioxide. But the question is, how many oxygen atoms are there? Well, now we're going to convert molecules to oxygen atoms. So the ratio of molecules to oxygen atoms is in the subscript. For every 1 sulfur trioxide molecule, you have 3 atoms of oxygen. That's the ratio. Now, if we multiply those out, we should get 1.44 times 10 to the 22nd, was it? No, 25th, excuse me. Atoms of oxygen in that many moles of sulfur trioxide. So a lot of these problems we've been doing are purely dimensional analysis. Unit conversions. All right, 49. 4 molecules of chlorine weigh. 4 molecules. All right, when you encounter a problem like this, there's one fact that you have to know. Otherwise, you'll get it wrong. What's a molecule of chlorine? Chlorine is one of the diatomics. Right? It's one of the diatomics like hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Those are all diatomic. So when the problem says chlorine, it means Cl2. Now we can answer the question. What's the mass of 4 molecules of chlorine? Well, we need to convert molecules to moles because that's our bridge. So we have molecules on the bottom, 6.022 times 10 to the 23rd molecules per mole. Then we convert moles to mass using the molar mass of chlorine. So we have 2 times the individual atomic mass, which is 35.45 grams per mole. Right, and that's 70.90 grams per mole. Right, molecules cancel, moles cancel, leaves us with mass. That answers the question. Right, so if we do the calculation, hold everything. The answers are in 2 different formats, either grams or atomic mass units. All right. So we've been calculating grams. So how many grams is this? Let's see if it's one of the answers. Let's see. 4, 6.022, 23, 5, 70.90 times. All right, this would be 4.71 times 10 to the minus 2, 22 grams. Now, if we had the conversion factor, we can convert grams into atomic mass units. Right? We encountered that in the lecture. But we shouldn't have to do that. If we're going 4 molecules, what's the atomic mass unit per molecule? Right? That number is the same number as grams per mole. So for chlorine, it will be 3545 times 2. It would be this. So it's 70.9 grams per mole. It's also 70.90 atomic mass units per molecule. Right? So if we ignore these and say this one times that one, molecules cancel, 70.90 times 4 is the other option we have. 284 atomic mass units. That's why the answer is C. Right, so it pays to look at the answers to see, I mean, the question should very often gives you, the problem gives you the correct question for presenting the answer. But sometimes you have to look at the answers, especially in these multiple choice questions, to see what form the answer occurs. So we had the choice, either grams or atomic mass units. Grams doesn't work. Atomic mass units does. All right, 49, 53. Which represents the greatest mass? Well, notice we got 1 mole of each in the answers. We got 1 mole of iron, aluminum, rubidium, and titanium. One mole of each. Okay. So if you got 1 mole of each, all we need to know is the molar mass of each one to figure out which one has the greatest mass. And so go to the periodic table. Iron is 5585 grams per mole. Aluminum is 2698. Rubidium is a big one, 8547 grams per mole. And titanium is 4787. Right? So if they're all 1 mole, so we just have to pick the heaviest one right there, rubidium. Okay. Let's see, down to 61. A sample of metal weighing 2.59 grams is combined with oxygen. The metal oxide weighs 3.01 grams. The mass percent of oxygen in the compound is. All right, let's see. What do we have? What information? We're looking for the mass percent of oxygen. We want the percent, oxygen percent by mass. That's what we're after. Okay. We're given 2.59 grams. 2.59 grams of the metal. Some metal is combined with oxygen. All right, so we add this together with oxygen and gives us the metal oxide. Right? And the metal oxide now weighs 3.01 grams. 3.01. Okay. All right. So remember, we know the mass of the metal, and we know the mass of the metal oxide. What's the mass of the oxygen? It's the difference. So 3.01 minus 2.59 is, let's see, 4, that's it, 0.42 grams is the mass of oxygen. Okay. Well, what's the percent calculation by mass? That's equal to the mass of oxygen, 0.42 grams, divided by the total mass, times 100. So I'm going to calculate this one just to give me some practice. So I get 14%. Yeah, 14%. Oxygen by mass. So the answer is E. Okay, 62. Let's see, what's the molar mass of nitroglycerin? All right. I mean, it looks like trouble, but it's really not. You just follow the same procedure as always. C3, H5, and then the nitro part, NO3, taken 3 times. And that's nitroglycerin. Okay. Nitroglycerin is actually those 3 carbons hooked together. And then we have nitrate here, nitrate here, nitrate there. Okay. And the rest of it is hydrogens. We have a hydrogen here, a hydrogen there, there. 1, 2, 3, 4, 5. 3 carbons, 3 nitrates. That's the molecule. This is glycerol. It's the foundation for fatty, all true fats that are in your body. Instead of nitrate, though, we put a fatty acid out here. Okay, a triglyceride. Anyway, you don't need to know that to solve the problem. The question is, what's the molar mass? Well, we need 3 carbons. We need 5 hydrogens. We need 3 nitrogens. And we need 9 oxygens. Add those together. And we should get 227 grams per mole. 62. 63. A certain compound has an empirical formula of NH2O. NH2O. That's the empirical formula, right? Its molar mass, or the true molar mass of the compound, is between 55 and 65. What's the molecular formula? All right, so what we need is something here, the multiplier. But in order to find that, we need to know, what is this empirical mass? So we have 14.01 plus 2 times 1.01 plus oxygen. Right? All right, so let's see what that is. Uh, 3203. 32.03 grams per mole of that formula. Okay? We know that the molar mass of the true compound, which incorporates that multiplier, is between 55 and 65. So the true molar mass is between 55 to 65. All right? If N is equal to 1, then we're saying the molar mass is 32. That doesn't work. What if N equals 2? Then we have, 64.06. That's better. That fits right in here. Okay, so if N equals 2, then the formula is N2H4O2. All right, B, N2H4O2. And let's see, 64. The molar mass of blood sugar, which is glucose, C6H12O6. Okay. Is what? We just have to calculate it. Right? 6 times 12.01 for carbon, 12 times 1.01 for hydrogen, and 6 times 16 for oxygen. And then add them together. Okay, so I'm going to defer, and 180.16 grams per mole. All right, what's next? 67. Determine the percentage composition by mass of lead in this compound. Right, so we just need to know the molar mass of lead. Percent of lead is 207.21, 207.21, and that goes in the denominator also, plus 2 times fluorine, which is 19, times 100. If I do the calculation, I should get 84.5% lead by mass. Okay, that was 67, 75. Calculate the number of moles of water molecules in 72 grams of water. 72 grams of water. The question is the number of moles of water molecules. And so all we need is the conversion from grams to moles. Okay. Grams cancel, leaves us with moles. There's the molar mass of water. So 18 in the 72 is about 4. Right? About 4. There it is, 4 moles. Okay, that was simple enough. There is some redundancy in here. I just think you need as much practice as possible. 77. Determine the percentage composition by mass of oxygen in Li2SO4. And we want percent composition of oxygen. All right, so we need 4 oxygens and 4 oxygens plus a sulfur, which is 3207, and 2 lithiums, which is a very light atom, 6.94. There we go, times 100. And if we do our calculations correctly, we should come out with 58.21%. 77. Right. 78. 78. A compound is analyzed and found to contain 12.1% carbon, 16.2% oxygen, and 71.7% chlorine by mass. What's the empirical formula? All right, we have to assume that those are the only elements in the compound. And to be sure, we just take, let's see, 12.1% carbon and 16.2% oxygen. And then chlorine is 71.7%. If we add those up, we get, let's see, 0, carry the 1, 2, 8, 10, 7, 8, 9, 10, 100%. Okay, so that confirms that these are the only 3 elements in that compound. Now they want to know the empirical formula. Okay, so we have to assume 100 grams sample. That's 12.1 grams carbon, 16.2 grams oxygen, 71.7 grams chlorine. We're going to convert them, each one, to moles. Right. Carbon is 12.01. Oxygen is 16. And chlorine is 35.45. Now I could take a shortcut here. It might lose some of you, but this is almost, this is about 1 mole. This is about 1 mole. This is about 2 moles. But if we do the calculation, then I can prove it to you. So 12.1 12.01 divided into it is 1.007 moles. And 16.2 enter and 16 divide is 1.0125. 3. Okay. And then 71.5 divided by 3545 is 2.017. 2.017. These are each so close to whole numbers that we can say this one is approximately 1, approximately 1, approximately 2. So the empirical formula would be carbon, oxygen, chlorine, 2. COCl2. That's A. This is the kind of problem that you would see on a standardized chemistry exam, like from the American Chemical Society. So that you don't need a calculator to do the calculation. You just need to remember certain values, have a periodic table, and you can estimate close enough to get the answer. And that happens quickly. It's testing whether you know what you're doing, not that you can just punch numbers into a calculator. The test is, were you paying attention in class? Okay, 83. You have 12.6 grams of an unknown substance A. 12.6 grams of A. 35.0 grams of chlorine gas. 35.0 grams of chlorine gas. Substance A contains 1.5 times as many molecules as chlorine. So this one, we can actually say molecules are moles. Actually, moles of A equals 1.5 times moles of chlorine gas. Okay, what's the identity of A? Well, we have the mass. Unknown substance A. So it doesn't even tell us if it's an element or not. Let's see what we can get from it at this point. Right? This many grams is how many moles? Well, we need the number of moles of chlorine first. Before we can do this calculation, we need the moles of chlorine, grams per mole. So it's 35.45. So that's about 1 mole. 35 into 35 is approximately 1 mole of chlorine. So the moles of A equals 1.5 times 1 equals 1.5 moles. So 12.6 grams divided by 1.5 moles will give us the molar mass of the substance. All right, 12.6 divided by 1.5, which is 8.4 grams per mole. No, that doesn't help at all. Well, I say it doesn't help. No, it doesn't help. So that was the wrong approach. Let's see where I went wrong. We know that the number of moles of A is 1.5 times the moles of chlorine. So the moles of chlorine, let's calculate it out. Maybe that's where I made my mistake. Let's calculate exactly how many moles that is. 35, enter, oops, wrong. Why? Because there are 2 chlorines. This is 70.90. which is 0.494. Now we can say 0.494. Maybe I was on the right track. I just made a mistake. 1.5 times that, which is 0.740 moles of A. So moles of A, I think this is going to work better. 0.740 divided into 12.6 is 17.0 grams per mole. All right. Now we have to compare it with answers and see which one comes closest. So if we have A, B, C, and D, and E, yeah, and E. We should be able, they're probably far enough apart that we can just estimate. What, uranium hexafluoride? What does uranium weigh? Right, uranium is 238. 238 plus 6 times 19, right? That's nowhere near 17, is it? We don't even have to do that one. How about oxygen? O2 is 2 times 16, which would be 32, right? That's not it. How about C? Ammonia. So that's 14.01 plus 3.03 for the hydrogens equals about 17. That's the one right there. We could do the others, but we found the answer. All right. 83, 88. Calculate the percentage composition by mass of magnesium. We want percent magnesium in the compound magnesium arsenate, Mg3, and isn't that nice of them? They give you the formula. ASO4, taken 2 times. Okay, so what's the percent magnesium? Well, we need 3 magnesiums, which would be 2431. And then 3 times 2431 on the bottom, plus 2 arsenics. So arsenic, we look it up, 7492. 74.92 plus 2 times 4 is 8 oxygens times 100. If we do the calculations correctly, we should get 20.8% magnesium. $91. Okay, a compound is composed of element X and hydrogen. So we do know that this one is an element. X and hydrogen are in that binary compound. Now, I don't know whether the X comes first or the hydrogen comes first. We don't know that yet because we don't know what X is. If X is a nonmetal, then hydrogen comes first. If X is a metal, then hydrogen comes second. Analysis shows the compound to be 80% by mass of X. So this is 80% X. What does that mean? That means it's 20% hydrogen. And 3 times as many hydrogen atoms as X atoms. So that means for every one of these, we have 3 of those. Okay? Which element is X? All right. So how do we get at this? Well, we know how many hydrogen atoms are in that molecule. We know that there are 3. What if we have 100 grams of the sample? If we have a 100-gram sample, Then 20 grams is hydrogen. And we can calculate how many moles that is. So 20 grams of hydrogen, moles, and this is 1.01. So 1.01 into 20 is how many moles of hydrogen there are in a 100-gram sample. Remember, this ratio is fixed. Law of definite proportions. So that's 1.98 moles of hydrogen. Okay. How many moles of X are there in the compound? It was 1/3, right? Because the ratio is 1 to 3. So 1.98 moles of hydrogen converted to X. There are 3 of these for every one of those. That means we divide by 3 and we get 6.6 moles. Oh, excuse me. My mistake. Let's see if I did that right. Oh, no, this is 19.8. Sorry. That didn't look right. Divide 20 by 1 and you get 1 or 2. No, 19.8. So this is 19.8 divided by 3. Now that is correct, 6.6. That's moles of X. Okay, so now we know how many moles of X, and we know how many grams of X, right? 80 grams of X for 6.6 moles, right? Because with a 100-gram sample, 80 grams of it is X. So we know the mass of X, we know the moles of X. We can calculate its molar mass. And so 80 divided by is 12.1 grams per mole for X. Okay. We know how to identify an element by its atomic number. That's easy. Atomic number is unique for each element. But if you don't have the atomic number, what you may have to resort to is the molar mass. Fortunately, most of the elements in the periodic table have unique molar masses also. Well, their average atomic mass is fairly unique. There's some that are very close together, but most of them are separate enough. And all you have to do is take that number, look for it on your periodic table, and the closest one we come to is carbon at 12.01, right? So we've introduced some error here in the calculation. That's why it's not exactly 12.01, it's 12.1. But the best guess is carbon. That's D. All right, 94. You have 2 beakers on your lab table. Beaker 1 contains 32.07 grams of sulfur. All right, beaker 1 has 32.07 grams of sulfur. Okay, beaker 2 has 74.92 grams of arsenic. So beaker 2 has 79.02 grams of arsenic. Is that right? 79? No, 74.92, excuse me. 74.92 grams of arsenic. Which beaker contains the greater number of atoms? Well, let's see. Well, we just convert the number of atoms, right? For each one. Grams per mole, grams per mole. So for sulfur, it's 32.07 grams per mole. That's 1 mole of sulfur. How about arsenic? Arsenic is 74.92. That's 1 mole. So you got exactly the same number of atoms in each one, right? So which one fits? Well, let's see. Which beaker contains the greatest number? Well, neither one. B says beaker 1 and 2 contain the same number of atoms because there is 1 mole of each. That's the best answer. B. All right, 97. Convert 4.13 moles of PCl5. 4.13 moles of PCl5 into molecules. Now here again, that doesn't matter because we're going from numbers to a different expression of numbers. So this could be anything. So the magic number is moles on the bottom and molecules on the top. Right? And that's the question? Molecules, yeah. And the magic number is Avogadro. Right? So 4 times 6 is about 24, maybe a little over 24. Or 2.4 times 10 to the 24th. D is the closest one there. 2.49 times 10 to the 24th molecules. Okay. 97. $99. Let's see. Got a little over half an hour. Let me be sure I got enough time to finish this thing. Yeah, I think I do. I think I can finish it. 5.392 grams of hydrogen gas. 5.392 grams of hydrogen gas. Diatomic. Contains what? Let's see, we've got atoms, molecules, atoms of E is atoms of oxygen. If you're not paying attention, then you think that that's a valid answer, but if you got hydrogen gas, where's the oxygen? It's not in there. So we can throw E out right now. So we've got atoms or molecules. Right? So let's calculate the number of molecules first and see if that's one of the answers. And then if that's not it, then we can go to atoms of hydrogen. So molecules would be let's see, 2.02 grams because there are 2 hydrogens. So 5.392. 5.392. Let's see. Atoms and molecules. Oh, we need to calculate the molecules. So let's carry it. Let's carry it on to molecules now. Moles, molecules. 6.022 times 10 to the 23rd. That would be the number of molecules. 392. 2.02 divided into that and 6.022 exponent 23 times. So I get 4 significant figures. 1.607 times 10 to the 24th molecules of hydrogen. Let's see if that's one of them. 1.607 10 to the 24th. No, that's not. So let's go to atoms. 1.607 times 10 to the 24th molecules of hydrogen is how many atoms? For every 1 molecule, we have 2 atoms. All right. So 2 times that value is 3.215 times 10 to the 24th atoms. 3.215. Round it off. D, 3.22. Okay, so D is the answer to 99. $100. Okay. Consider equal mole samples of dinitrogen monoxide, aluminum nitrate, potassium cyanide. Rank these from least to greatest number of nitrogen atoms in each sample. Equal molar samples, equal moles of each one. All right. So we've got dinitrogen monoxide. That's laughing gas, nitrous oxide. Aluminum nitrate. Right. That's a minus. This is a 3+, so we need 3 of these. And potassium cyanide. There, those 3. The question is, rank them from least to greatest number of nitrogen atoms in each sample. Well, we've got equal moles. Right? Let's just, for argument's sake, say it's 1 mole. Right? So this would give us 1 mole of oxygen. This would give us 9 moles of oxygen. And this would give us, oh, nitrogen, excuse me. I got hung up on oxygen. Let's go back. Nitrogen. 2 moles of nitrogen. 3 moles of nitrogen. And 1 mole of nitrogen. So the order from least to greatest is potassium cyanide, dinitrogen monoxide, and aluminum nitrate. That would be E. Okay. Let's see, 101. Calculate the mass of 3.53 times 10 to the 26 atoms of silver. 3.53 times 10 to the 26th atoms of silver. We want to know the mass. So remember, we got to convert it to moles first. So we got to cancel atoms in the denominator. That gives us a mole here. Now we can convert moles to grams for silver, which is 107.87. Right? Moles cancel, atoms cancel. That'll give us our answer. And it should be 6.32 times 10 to the 4th. Grams. All right. 101. Scroll. 106. The mass in grams of 3.52 moles of nitrogen gas. 3.52 moles of nitrogen gas. And we want the mass in grams. That's fairly simple. Moles on the bottom, grams on the top. Cancel the moles. How much does a mole of nitrogen gas weigh? Well, 1 atom is 14.01, so 2 would be 28.02. Right? So 28 times 3.5. 3 times 8, 24, 2, 6, 8, 80 and a half. That's about 90 something. At 98.6. I wonder if they chose that on purpose. 98.6 grams. Substitute degrees Fahrenheit, you got body temperature. I bet somebody was being clever. $110. Calculate the molecular formula of a compound with empirical formula CH2O. CH2O is the empirical formula. And a molar mass of 180 grams. 180 grams per mole. That's the molar mass. What's the empirical mass here? Okay. 12.01, 2.02 for hydrogen, and 16 for oxygen. So that's 3, 0, 6, 7, 8, 9, 10, and 2, 3. 30.03. So 30.03 divided into this is approximately 6. So that means N equals 6, and this would be C6H12O6. Glucose. $113. A 60.2 milliliter sample of mercury contains how many atoms of mercury? All right, you're given the density, and you are going to need that because you can't calculate how many atoms of mercury you have until you know how many grams you have. Then you can convert using molar mass. But we're given milliliters. 60.2 milliliters of mercury. We want to convert that to grams, so we need milliliters on the bottom, grams on the top. And the magic number is 13.6. Okay, that converts to grams. Now we're going to convert to moles. Right? How many atoms? So we got to get moles first. Mercury is 200.59. Right? That gets rid of grams. Now we convert moles to atoms. Six 6.022 times 10 to the 23rd atoms. And then we just run the numbers. This one times that one divided by this one will give you 2.46 times 10 to the 24th atoms. Okay, that's 113. 116. Okay. Vinegar contains carbon, hydrogen, and oxygen. That's it. And the percentage of each is 40% carbon, 6.7 hydrogen, and the remainder is oxygen. If the molar mass of vinegar is 60, what's the molecular formula? All right. So let's say 40.01% carbon. Hydrogen then is 6.7%. 7%. And how much is oxygen? Well, it's 100 minus these two. You have to calculate that yourself. 40.01 and 6.7. 100 minus that is 53. 53.29. That should add up to 100%. Okay, so now that we have the percent composition, we can calculate the empirical formula. We have to assume 100 gram sample. So that means we have 40.01 grams of carbon, 6.70 grams of hydrogen, and 53.29 grams of oxygen. Now we can convert each one. Man, that one's running out. Let's try this one. Grams on the bottom, moles on the top. So for oxygen, it's 16. For hydrogen, it's 1.01. For carbon, it's 12.01. So let's find out what the mole ratio is. It's going to be fractional, but that's where we start. So 40.01 divided by 12.01 is 3.33 moles of carbon. 6.7 divided by 1.01 is 6.63 moles of hydrogen. This is carbon, hydrogen. And 53.29 divided by 16 is 3.33 moles of oxygen. Okay, now we want to get whole number ratio. So we divide through by the smallest one, which is either this one or this one, it doesn't matter. 3.33, 3.33, and 3.33. This is equal to 1, this is equal to 1, and that's equal to 2, should be. Yeah, 1.99. Okay, so there's the empirical ratio of carbon, hydrogen, and oxygen. We need that value. We're told that the molar mass is 60. So the actual value is 60, that's it, grams per mole. So what's the empirical mass? Well, it's 12.01 and 2.02 and 16. 3, 0, 6, 7, 8, 9, 10, and it's 30. So this is 30 grams per mole. Divide this by 30. N equals 2, and it's C2H6O2. Oh, excuse me. That's not right. 4. Right. 242. A is the answer. Now, since acetic acid needs a proton, right, a hydrogen in front, we normally write it this way. Put one of them out here, and then put the rest of it back here. That's the way you'll see it in your list of acids. Because this is the acetate polyatomic ion, and there's the proton that makes it acidic. Other times you may see it written this way. Right? It's the same formula arranged to give you a little bit of idea about the structure. Because the structure of acetic acid has this carbon out here with hydrogens on it. Then it has a carbon here with an oxygen there and an oxygen here and a hydrogen there. That's the acidic hydrogen there. So these are all three the same compound, written different ways. And the only reason I gave you that one is because you might see it that way sometimes. All right. Is that it? That's it. Let's see. Now we have this information. All right. We have this information, polyatomic ions, empirical formula instructions, and a periodic table. So you will have those either in person if you come to class, or if you take the exam in Brightspace, you'll have a separate document, useful information. Be sure and print that out before you take the exam, and it will have that information in it. Okay. That's it for our review for Chapter 8. And the exam for Chapter 8 will be next Thursday. Let's see if we've got anything else planned on that day. Let's see, 12, 15. Yes. So we're going to have the exam next Thursday, the 15th, right? 15th, yeah. And then I'm going to introduce new material in Chapter 6, which will be chemical reactions. And then the following Tuesday, we'll get reactions in aqueous solutions. So there are going to be 2 chapters for the next exam, but only this chapter, 1 chapter for exam number 3.